Okay, Meredith, Grace, okay. Julian, you got the same answer. Very good. Yeah, because if you think about this, your square root of 0 is going to be 0. So you're basically doing 5 minus square root of 0 or 5 minus 0, which will of course give you 5. Same thing for 5 minus square root of 1. That would be 5 minus 1, which will give you 4. 5 minus square root of 4. Square root of 4 is 2. So that's 5 minus 2, which gives you 3. And of course, just repeat that for all of the other x values. 5 minus square root of 9 is 5 minus 3, which gives you a 2. And then 5 minus square root of 16 is 5 minus 4, which gives you a 1. So, you can kind of work it out, put it in your calculator, however you're comfortable. So I'm actually going to go ahead and erase our graph over here. We don't really need that. And let's see. So you are going to be at 0, 5. So right up here. Positive 1, positive 4. Positive 4, positive 3. Positive 9, and positive 2. And of course, we won't be able to graph our 16 in here, but you still get the general idea of what the shape of this graph is going to be. And because of that reflection, your graph is now opening down, right? Instead of opening up like we saw with the base function. So this would be our function over here. But you know what? This is not enough, because like we did yesterday, we need to know where this graph would be crossing our x-axis at. So we need to know where it's actually crossing the x-axis at. So find your x-intercept here basically. And remember, to find the x-intercept, we make our y value 0. So you're basically setting the 5 minus square root of x equal to 0 and solving for x. So when we solve for x, what value are we looking at for the x-intercept?
25.
Actually, no, Julian, it wouldn't be 5. Because you have that square root in there, right? So when you actually solve this, again, you can start by moving the square root of x to the other side. So we can go ahead and add that. You would end up getting 5 equals, of course, positive square root of x. And then what would we do to get rid of the square root?
Square it.
Yeah, very good. So we would need to square, excuse me, we would need to square both sides of our equation. So the square and square root would cancel out, leaving us behind with x, and you would end up getting x equals 25, right? So that means our graph will be crossing the x-axis at positive 25. Now you have two options to try and graph this function. So you can either just go ahead and extend your x-axis, make that right-hand side of your x-axis longer so you can see where the graph crosses, or your other option would be to redraw the graph and probably rearrange the scale on your axes over here. So that's exactly what I'm going to do. So what I'm actually going to do is rescale my graph over here, and I'm going to do this in terms of 5s. So you can think of the first marker here being 5, 10, of course 15, 20, and 25. So my 25 will basically be the 5th marker over here. Okay, so I'm just going to rescale my x-axis, and typically you would rescale the y-axis also, but I am going to leave the y-axis just in once. This is probably going to be a very weird looking graph, but you would get the idea of what this graph is going to look like. So this is kind of what, just as a zoomed out picture of our graph should look like. And let me show you on Desmos just to give you a better idea of what this graph could look like. So we've got square root of x, and if we zoom out, hopefully you can see right there. So we start at 5, we're going to cross the x-axis at 25, and then of course you will see the arm of our graph is now going to head downwards. Okay, so now comes the idea of what is our solution set going to look like. So let's take a look at that. Remember, our original inequality was asking where is 5 minus square root of x going to equal 0 or be greater than 0, right? So they want to know where your y values are equal to 0 and greater than 0. So let me, okay, so obviously all the y values that are above the x-axis, our y values are going to be greater than 0 in this section. Right at the x-intercept, this is where your y value is equal to 0, and you can kind of see that in the ordered pair here. And then once your graph falls below the x-axis, this is where all the y values are going to be negative. So when your graph is above the x-axis, that's where we know all the y values are positive. Right on the x-axis, so that's your x-intercept, is where y values are 0. And then the moment you fall below the x-axis, that's where all the y values are going to be negative. So since this inequality is asking us specifically for where it's going to be equal to 0 and greater than 0, we of course need to use that first part of our graph, right? From the point where it's starting at the y-axis until it reaches the x-intercept. So does anybody have an idea how we would write that in interval notation? Remember, the interval notation is always written with respect to the x values, the x-axis. Okay, let's see, Grace, you've got 0 to 25, including the endpoints, okay? So what do you guys think? Is that the correct answer, or do you have a different answer than what Grace has given us? Because again, remember, like I said, we are looking at this in terms of the x-axis. Okay, Lori, you're going from 5 to 25, okay? And we can take a look at that as well. So basically the idea is you're looking at the x-axis to see what these x values are, where the graph is going to be. So when you look at your graph over here, this is where, you know, on the x-axis, our graph is starting at. So if you look at this ordered pair, where my graph begins, this ordered pair is actually going to be 0, comma 5, because your x value at that point is 0, right? Because you're right on top of the y-axis. So you're going from 0, 5, the ordered pair 0, 5, all the way to where the x-intercept is, which is the ordered pair 25 to 0. So Lori, the 5 is actually the y coordinate, not the x coordinate. Your x coordinate at that point is technically 0. So the interval notation that Grace gave us is actually what your solution set is going to be. Okay, very good. So in this case, yeah, your solution set for this inequality, 5 minus square root of x greater than equal to 0, your solution set is going to be starting at 0 and going to 25. Now remember, we are using that bracket on 25 because you have the greater than and equal to inequality. If they didn't have the equal to as part of that inequality, then you would have put a parentheses on 25. You would have still had a bracket on 0 because, you know, obviously 0 is included in our solution set. So it really depends on what kind of inequality you are looking at here. Now, even though they're not asking, but just to make sure you are comfortable with our domain and range information, can you go ahead and tell me what the domain and range for this function is going to be? 5 minus square root of x. So on the x-axis, where is our function starting at and where is it going for the domain? Okay, Lori, you've got 0 to negative infinity. Julian, you've got 0 to infinity, including 0. Okay, so Lori, I think you're getting a little bit confused with the domain and range, because if you just look at the graph in terms of horizontally where it's going, you can see it starts at 0 on the x-axis and then it's headed to the right-hand side, right? It's going to the right, and that's in terms of the x-axis. So in terms of the x-axis, your graph is actually headed towards positive infinity. So it does start at 0 and it goes to the right on positive infinity. Okay, very good. And then Clinton and Meredith, you guys also have the right answer. Okay, very good. Evelyn as well. All right, good job, guys. So can you tell me what the range for this function is going to be now? Clinton, you've got negative infinity to 5. Julian, same thing, okay, including 5. Yeah, very good. Because now in terms of the y-axis, obviously you can see this curve of our graph is headed downward. So it's definitely going down, which means in terms of the y-axis, it is headed towards negative infinity. Now remember, when you're writing interval notation, we put the smaller number first. So that's why we write negative infinity first. And of course, you can see our graph stops at 5 on the y-axis. There's no graph above 5. So that's why you are stopping on the range at 5. And of course, we include 5 because we do have a point at 5. So yeah, your range is going from negative infinity to 5. Very good job, guys. Meredith, Clinton, Julian. Very nice. All right, so this was our last example that we needed to talk about in section 2.3. So do you guys have any question on this example? Nope. All righty. So let's move on to our next section here, which is 2.4. So as you can see, 2.4 here, we are talking about operations with functions. So basically looking at how we can add, subtract, multiply and divide two functions or maybe even more. And we'll also talk about what we call as composition of functions. So let's start with our operations over here. So if you look at this green box over here, we're defining what the sum, difference, product, and quotient are going to be. So when they're talking about adding two functions, so when they say f plus g of x, that basically means you take the f function and add it with the g function. Same thing for subtraction. When they're saying f minus g of x, that's going to be f of x minus g of x. Pretty much that same definition follows for multiplication and division. When it's f times g, again, you take the two functions and multiply them together. Now with division, order is going to be important. So since it says f divided by g, that means f is going to be on the numerator, g is going to be on the denominator. Now we still have to consider the fact that anytime we divide anything, if your denominator becomes a 0, your division or your quotient would be undefined. So we actually have to put a restriction on the bottom function. And so we say as long as the bottom function is not going to be equal to 0, you should be able to find the quotient of functions. If your bottom function is going to be equal to 0, then we will need to place some restrictions on that bottom function. And we'll actually look at an example for that here. So just performing some basic operations here, you can see we are defining our h and j functions over here, and they're asking us to find these different operations. So let's take a look at how we can go about solving this first one over here. So we are given h of x as x squared, and we are given j of x as 3x. For the first part, they're asking us to find the sum of h plus j. But this one, they're actually asking us to find it specifically at number 5. So using your definition that's given to us here, for the sum function, that actually means you will be taking the h function evaluated at number 5 and adding it with the j function, again evaluated at the number 5, which means we need to go to each one of our h and j functions and plug in for the x value the number 5 and see what answers we come up with. So when you have h at 5, what will that answer come out to be? Because h of 5 means you are going to be doing, h, remember, is the x squared function, so that means we will be doing 5 squared. So what will that end up giving us? Yeah, very good, 25, which means you're going to be using that answer 25 over here. And then we'll need to do the same thing for j of 5. And for j of 5, what will we get? Yeah, very nice. We will end up getting 15 because that means you're doing 3 times x, which is 3 times 5. And 3 times 5, of course, will give us 15. Okay, I'm not sure what this guy is doing today. And when you add these two numbers, what do you end up getting? Yeah, very good, Audrey. And I don't know why my pen does not want to write today. Okay, so that's all you are basically doing. You're taking each function individually at 5. You come up with what those answers are going to be, and then basically just add them together to get your answer. So let's see. For part B, they want us to do multiplication here. So that's going to be h multiplied by j. H multiplied by j. Again, same thing. This time they're evaluating at the number 2. So that means we will be taking h of 2 and multiplying it with j of 2. So can you tell me what h of 2 will come out to be? And j of 2 as well, obviously. Okay, yeah, because for h of 2, you will be doing x squared, which is 2 squared. So 2 times 2 will give you 4. And then for j of 2, that's of course going to be 3 times 2. 3 times 2 will give you 6. Very good, Audrey. And then of course you just multiply those two numbers. So 4 times 6 will end up giving you 24 as your answer. Alrighty, yeah, very good, Lori. Okay, very nice. So let's see what was part C asking us to do. So part C is h divided by j at the value of a. So let's see, h divided by j evaluated at a, which means we are doing h of a divided by j of a. Oh, come on, buddy. Okay, so remember, this time we're not using a number, but we're just using a instead of x. So if h of x is x squared, which means h of a will become, of course, a squared, right? Because you just replace the x with the a. And then for j of a, that would be 3 times x, so that would become 3 times a. So we would have 3 times a on the denominator here. Now, can you tell me what our simplified answer would look like once we simplify this fraction, a squared over 3a? Very nice, Meredith. Yeah, it will simplify into a over 3, because if you think about this, the a squared on the numerator is basically a times a, and then you have 3 times a on the bottom, so you can cancel out one of those common a's, leaving us behind with a over 3, and there you go. That would be your simplified result over here. Alrighty, very nice. And then the last one was talking about h minus j they're evaluating that at x itself. So h minus j at x will basically be h of x minus j of x. So again, your h of x is the x squared function, j of x is the 3x function, so that would be minus 3x over here. And you can leave it this way, or you can actually simplify it. So can you tell me what this guy would simplify into? X squared minus 3x. X over 3? No? Because there's no division happening here, right? Yeah, so the only thing you're actually missing there, Meredith, is the x minus 3 should be in parentheses, and then you should have that common x outside. Yeah, very good, Morgan. That's kind of what I was looking at. Because in both of these terms that we have, x squared minus 3x, of course, you can see that x would be common between both of these terms. So we can actually take that x outside as a greatest common factor. And then from the first term, you would have 1x left behind. From the second term, you would have a 3 left behind. So you can, like I said, leave the answer like this, or if they want a simplified answer, you can go ahead and factor it out. Okay, so just some examples where they are actually using numbers to evaluate, like they did in parts A and B, or they're just using variables to evaluate your functions. So did any of you have any questions on this example? Okay, let's take a look, oh, not you, at our next example over here. So they're talking about, before we get into example 2, they're talking in terms of the domain of the function. So they're saying the domain for the f plus g, f minus g, f multiplied by g, and f divided by g is going to be the intersection of the domain of the f function with the domain of the g function. So that's going to be the domain for all 4 of these functions, with the only exception that for the domain of the division, the quotient function, the f divided by g, you would need to exclude any values or any x, values for the x variable, which would make your denominator 0, which would make your g of x function 0. So we would need to remember to exclude those from our domain for the bottom function, basically. And your bottom function will be different depending on what letters they are using. So let's go ahead and talk about what we think the domain should be for example 2 over here. So you can see we're giving you sets of ordered pairs instead of equations. So this idea can kind of make a little bit more sense. So if we just talk about what the intersection for the H and J domain would look like. So the intersection of the domain of your H and J functions. So if you look at just the domain for the H function, remember again in the set of ordered pairs, that's just all your X values. So for domain of H, we would have 2, 4, and 6. If you talk about the domain of the J function, for the J function, it would of course only be the 2 and the 6 we have here. So when we talk about the intersection, what do you think is going to fall in the intersection over here? And remember, we had talked about the intersection of sets in section 1.7 when we had talked about the interval notation and how to solve inequalities. So you're using that same idea of intersection, which basically means that only the elements that are common between the two sets make it into the intersection. Remember that union is where you bring everybody and put them together, but intersection is only those terms that are common. So what do you think the intersection for these two domains will have? Very nice, Evelyn. Yeah, exactly. Because the only numbers common between the two sets are 2 and 6. So 2 and 6 is what the intersection is going to be. Now they're asking us to find the h plus j and the h divided by j functions. And then for each individual function, they want us to tell what the domain is. So hopefully this intersection that we came up with should be the domain for both of those functions. But again, we actually have to go through the calculations to see if that is going to be true or not. So let's go ahead and take a look at what kind of results we get when we try to work through example 2 over here. Okay, so we have, let's see, the h function is defined as 210, 40, and 68. The j function is defined as 25 and 60. Okay, and we know the intersection for the domain is going to be, and I'm going to write it using our set notation. So for the domain of the h function intersected with domain of the j function came out to be 2 and 6, just what we had as our result over here. Okay, so let's see what we can come up with. So the first one, they're asking us to find h plus j. Now this is the interesting part, because when they're saying find h plus j, that means you have to go through each individual ordered pair to come up with this. Okay, so to find the h plus j, you would be taking, you can see, since our intersection has 2 and 6, those are the two values we would be using to find this h plus j function. So you would be taking h of 2 and adding it with j of 2. So that would end up giving us, of course, h of 2, which means you go to the h function, find the ordered pair where your x value is 2, which means your y value is going to be 10. So that would be h of 2 is 10, right? And then for the j of 2, same thing, we would go to the j function and find the ordered pair where the x value is 2, which means your y value would be 5, and you end up getting 15. So this ordered pair would then end up being, we started with the x value of 2. Once we did all the math, our final answer came out to be 15. So that's actually part of your h plus j function. So we did it at number 2. Now we need to repeat the process at 6, because again, from the intersection, we know that is going to be our only other common number between these two functions. So what will h of 6 and j of 6 give us? Okay, so you've got 8 and 0. Clinton, you give me 8. Okay, so let's see. H of 6 is going to give us 8. Very good. And J of 6? Right? Will give you 0. So putting all these numbers together, I don't know, guys, what's happening with my hand today. It's not trying to cooperate. Okay, so H of 6 gave us 8. J of 6 gives us 0, which means, of course, your total is come out to be 8. So what's this ordered pair going to look like over here? Yeah, very nice. You started out with the x value of 6, and your final answer ended up being 8. So now we are ready to write our h plus j function. So the h plus j is again going to be the set of these two ordered pairs that we just came up with, which is going to be 2 and 15. And the second one is going to be 6 and 8. And then as you can see, the domain for the h plus j is the same as our intersection of 2 and 6. So this is our function itself, and then this is our domain. Okay, they are asking us to basically repeat the process with h divided by j. So let's do that next. So for h divided by j, of course, we would still need to use the same two numbers that we got in the intersection, which is 2 and 6. So let's look at 2 over here. So that's going to be h of 2 divided by j of 2. So h of 2 again is number 10 divided by j of 2, and j of 2 of course gave us 5. So 10 divided by 5 would give you 2. So what is this ordered pair going to look like? So for that h divided by j, what do we have? Yeah, very good. You will get 2 and 2. Now we repeat the process for the second number in our intersection, which is going to be 6. So that's h of 6 divided by j of 6. So h of 6 gave us 8. J of 6 gives us 0. And what will that end up giving us? So 8 divided by 0. No solution, yeah, because division by 0, as I told you earlier, is undefined. And so since it's undefined, you're not actually going to get an ordered pair, which also means that we cannot use 6 as part of our domain for the h divided by j function, because you are getting an undefined result when we try to do h of 6 divided by j of 6. So this guy we cannot use in our ordered pair, which means your h divided by j function is only going to have one ordered pair, which is that 2 comma 2, and which also tells us that the domain for this division is only going to have one value in it, which is this x value of 2, and that's all that h of j function is going to be. So in this case, like I said, with the ordered pairs, it kind of makes it a little bit more straightforward to see, okay, what numbers we can use and what we cannot use. And as you can see, because we are dividing by 0 over here, we cannot use 6 as part of our domain. And so from this intersection where you had 2 and 6, you can see for the h plus j, we were able to use both those numbers, 2 and 6. And of course, we got two ordered pairs based on those two x values. But when you came down to the division function, because j of 6 gives you a 0 as the answer, and you end up dividing 8 by 0, that's why we cannot include 6 in there. It's giving us an undefined answer. And so when they were telling us here in your handout that you will have to exclude from the domain of your division function any numbers which makes your denominator 0, that's exactly what we're doing here, because we cannot include this 6 because that 6 is making our denominator 0. Now we will have to keep this in mind even when you are looking at examples that may be given to us as equations instead of ordered pairs. So before we move on to number 3, do you guys have any questions on example 2 over here? Okay, so let's take a look at how we can work through example 3 over here. Okay, so we are given h of x is the function square root of x, and j of x function is just x. They're asking us to find h minus j and j times h and the domain for each of these. Okay, so before we talk about the domain and find the functions, let's go ahead and see what the domain for each individual function is going to be. So for domain of the h function, which is your square root of x, what will be its domain for a square root of x function? And we talked about square root of x extensively in the last two sections, both 2.2 and 2.3. So domain for square root of x. Very good, Julian. Yeah, because we cannot use negative numbers inside a square root of x. So your domain for h of x is going to go from 0 to positive infinity. Very good. All right, let's talk about the domain for the j of x function. Okay, this guy really is driving me crazy today. Okay, while I'm trying to get my pen to work, what will be the domain for the j of x function? Jack, very good. Yeah, negative infinity to positive infinity, because it's just a straight line with a positive slope. So you will be covering basically the entire x-axis here. Okay, so if we think about, what is the intersection between these two sets going to be? If it helps, you can kind of try and do a little graphing here. So for the j of x, of course, we are saying it's going to be the entire x-axis, whereas for the h of x function, we are saying you are only going from 0 to infinity, and of course, we are including 0. So what do you think the intersection of these two domains is going to be?
Would it be 0, infinity?
Very nice, Wyatt. Yeah, that's exactly what it's going to be, because obviously the domain of j of x is using the entire x-axis, but h of x is not. H of x is only going from 0 to infinity. So that's the only part that's going to be common between both our domains. So the intersection is going to be from 0 to infinity, and again, including 0. Yeah, very good, Clinton. So again, we want to see, will we be able to keep this intersection as the domain for the h minus j and the j times h function? So let's go ahead and take a look at those. So we are basically saying the intersection of the domain between h and j functions is going to be 0 to infinity. Okay. Alrighty, so let's do our first one, which was h minus j. And since we're, obviously looking at the equations here, we'll just do these at the x variable itself. So you are doing h of x minus j of x. So of course, h of x is going to be square root of x minus j of x is going to be x. Is there anything we can do to combine these or simplify this, or do we just leave it as it is? because you've got square root of x minus x. So is there really anything you can do to simplify? Yeah, Julian, you basically do have to leave it as it is. Evelyn, yeah, very good. Because, there's really nothing much we can do. This is not an equation. This is just the one side of your function. It's not like, we can move anything to the other side or simplify. So this will actually become what your h minus j function is going to look like. Now, when we talk about the domain for this function, you will notice the x on the right is an independent x. That x, of course, has no restrictions. But then we have another x here on the left side of our function, which is under the radical. So because this function, this x over here is underneath the radical, whatever restriction we put on this x is the same restriction that's going to go on the other one. So because of this guy being inside the square root of x, you will notice that this intersection of the two domains we came up with is going to be true for our h minus j function. Because of this guy over here, he has to stay from 0 to infinity, including 0. So that's going to become the domain of the entire h minus j function. So the domain is going to be similar to our intersection over here. So domain of h minus j function is going from 0 to infinity. Okay, so this guy, of course, worked out well with our intersection. Now, the next function they want us to find is the j times h. So let's take a look at what this guy will end up looking like. So j times h, again, at the variable x, will be j of x function multiplied by h of x function. Okay, so again, your j function, of course, is just x. Your h of x function is square root of x, so you're basically looking at x times square root of x. And again, like I was saying previously here with h minus j, since this is all on just one side of your function definition, you really cannot simplify this. So you actually just leave it again like it is over here. Now, what can you say about the domain for this multiplication over here? Will it be the same as the intersection, or will we have a different domain over here? Okay, Julian, you are saying intersection. So again, think about it like we were doing with the previous example. This x, of course, is on the outside, so it has no restrictions. But this x over here is still inside the square root symbol, right? And because it is inside the square root symbol, which means it will have the restrictions, you can only use numbers going from 0 to infinity, including 0. And so because of that, it automatically puts a restriction on the x on the outside. So yeah, you are going to have the intersection as your domain, again, for the j times h function over here. So in this example, you can actually see the intersection ended up being the domain for both of your functions. And honestly, if you think about this, guys, the only time you will have restriction on the domain is going to be for this quotient function. So for the addition, subtraction, and multiplication, you are going to get the intersection of the domain as the domain for those functions. It's only going to be the quotient function that we will need to be careful about, because anything that would make the denominator 0, we would need to exclude that. And as you can see in example 2, we had a division function in there, and we ended up coming up with a restriction just based on the example we had. But here in example 3, you had a difference and a product function. So you were actually not dealing with a quotient function. We were not doing a division. So coming up with a restriction was really not a likelihood that would happen in this case. And of course, you will have more examples in my math lab, so just work through them, and of course, let me know if you guys get stuck on anything. So those were the operations. Again, we're adding, subtracting, multiplying, and dividing our functions to come up with these results. But now we're getting into what we call as composition of functions. And composition of functions basically is, as you can see in that little statement underneath the heading, where basically you take the result from one function and it becomes basically the input for the second function. So you are literally taking one function and putting it inside of the second function. Kind of think about it. Step one, the result you get from step one is going to be the input for your step two. So you use the answer from step one and use it to come up with the answer for step two. So that's kind of what happens in these composition of functions. So they are saying, if you look at the green box here again, we have two functions, f and g, and we actually use this little notation over here with an open circle, f of g, which is how you read this. I'm not sure if they gave us instructions here, but basically these notations are how you would read this as f of g. For the other one where they are changing the order, you've got g in the front, f as a second function, you would read that as g of f. So basically we have f of g of x, which is defined as f being the outside function and g becomes the inside function. So you're literally taking that g function and you're going to put it inside of the f function. When you change the order and make it g of f, that means g will now be the outside function and f will now become the inside function. So obviously, we always start by solving the inside function first. You solve the inside function, you get the answer from it, and then you use that answer to solve the function on the outside. So you're working from the inside out as you're working through these composition examples. Just to make sure we understand the difference, like I said, we use a little open circle when we're talking about compositions, but you use a little dot when we are talking about multiplication. So multiplication is where you take the both of the functions and you multiply them together, which is different from composition, because composition, you, like I said, you take one function and put it inside of the other function. So just to understand the difference between the product function that we just talked about and the composition that we are looking at. And this is a neat little illustration that your textbook has in terms of how these compositions work. So basically they're kind of starting out with what the domain of our composition should be, which is the f of g. So whatever x value you use from this domain, that will go inside the first function, the inner function. You solve that, you come up with your answer, and then whatever answer you come up with, that's the answer you're going to put inside of that outer function, the f function in this case, because you are doing f of g over here, and you can kind of read that here in this little statement over here as well. So let's take a look at how these compositions actually work. So again, we're starting out with an easier example of using ordered pairs, and then we'll come back and do an example with the equation. So let's start by number 4 over here. So we are given the f function as the set of 2, 0, 4, 0, and 6, 8. We are given the g function as the set of 0, 7, and 6, 0. They're asking us to find g of f. So remember that order is important. When they're saying g of f, g is going to be the outside function, f is going to be the inside function, and then they want us to find the domain for that composition. So let's take a look at the g of f over here, which of course means g on the outside, f on the inside. Okay, So since f is on the inside, we start going through the f function values first. So that means we would be starting at the first ordered pair for our f function, which is starting at 2. So we start with f of 2. Now, of course, when we're talking about f of 2, that means you go to the ordered pair where you have 2 and look at the answer for the y coordinate, which is going to be 0. So the answer for f of 2 is of course going to come out to be 0, right? So you get 0 as the answer. So this is the result we get from solving the inside function. And now this answer becomes the input for our outside function. So once you get down to g of 0, you are now moving on to the g function and finding the ordered pair where your x value is 0, which would of course be this first ordered pair. And then looking at its y coordinate, you would of course have the answer 7. So g of 0 is actually going to give you the answer 7. So basically the idea is we started out with the x value of 2, which was coming from that f of 2. So that was our ordered pair where we started out at. And by the time we went through the composition and came up with the answer, we got 7 as the answer. So this is the ordered pair, the first ordered pair at least, for our g of f function. And of course, we'll need to go through all the other values in the f function to see how many ordered pairs we come up with. But before I move on to the other calculations, I kind of want to make sure you are understanding the idea of how composition works. So start with the inside function. And in this case, since we're looking at ordered pairs, we started with the first ordered pair, got the answer from that. That became the input for our g function. And then we went to the g function to find the answer. So let's repeat that for our second f ordered pair. So this time we will be doing, we've already done the 2. So let's move on to the 4 over here. So that would be f of 4. And of course, f of 4 is giving us 0 as the y value. So that will now become f of 4 gives us 0, which means for the g of 0, we go back to the g function. And again, looking at that same ordered pair, g of 0 will give us the answer 7. The g of 0 will also become 7, giving us the ordered pair. We started out with 4 and we ended up with 7. So this is our second ordered pair for the composition. And we've got one more f ordered pair, I guess. So we again start with f of 6 this time. And 6 will of course end up giving us the answer of 8. Right? So we get 8 from that. So now you will end up getting g of 8. And once you have g of 8, you need to go to the g function. But when you go to the g function, what do you notice?
There's no 8.
Yeah, there is no 8. Exactly. And Lori also sent that on chat. Yeah, very good. So we have no 8, which means we actually cannot go any further because we have nothing in the g function where you have an ordered pair with 8 as your x value, which means you actually just stop right here. So our composition is going to have, for the g of f function, you will have your two ordered pairs, which was at 2, 7 and 4, 7. So that's going to be your composition. Just using these two ordered pairs will give you the composition for g of f. So what can we say about the domain for this composition function then? So what would you put in the domain of the composition? Yeah, very nice, Clinton. It will be 2 and 4 because those are the only two ordered pairs we came up with. So since you only have the 2 and 4 in your function definition for the x values, those 2 and 4 become your function definition. Alrighty, and I think that's what they were asking us to do, was find the composition and state the domain. So before we move on to the next example, do you have any questions on number 4? No? Okay, so let's take a look at how we can do the same thing, but now using equations instead of set of ordered pairs, and what will that give us as a result. So let's look at number 5 over here. So we are given g of x as the function square root of x minus 1, and you are given h of x as 2x. And this time they're actually asking us specifically to evaluate these compositions at x equals 5. So the first one they're asking us to do is g of h at 5. So that actually means, again, g is going to be the outside function, and h of 5 will be the inside function. So what this means is we actually go to the h function first, find out what h of 5 is going to be, and then use that answer to come up with the value for g. So whatever that answer comes out to be. So what will h of 5 come out to be? Alrighty, Grace, you've got 10, Quentin 10. Yeah, very good. Because you're basically doing 2 times 5, which will give you the answer 10. So remember, this 10 is now going to become the input for your g function. So now we go to the g function, and of course we calculate what g of 10 is going to give us. So what will that come out to be? Okay, Clinton, you got 3. All right, let's take a look at that. So your g function is square root of x minus 1. So square root of x minus 1, of course, would be 10 minus 1 in our case, which would be square root of 9, and square root of 9, of course, ends up giving you 3. Yeah, very good. So in this case, you can see we actually started out with the x value of 5, and by the time we got through the composition, we get 3 as our answer. So that's what they're looking for here in this case. So this would be our answer. If they ask for an ordered pair, then you can, of course, put this in. Now, the second thing they were asking us to calculate is just by switching the order of our composition. So now they're asking us to do h of g at 5. So let's see what happens when we change the order of our composition. So h of g at 5 means h is now the outside function, and g of 5 is now going to be the inside function. So what will g of 5 give us? Clinton, you've got 2. Julian as well. Okay, let's take a look at this. So that would be square root of x minus 1, which again in this case would be 5 minus 1, square root of 4, which gives you 2. Very nice. And so of course that means the 2, oops, sorry, will now become the input for the h function. So which means we are now calculating h of 2. And again, guys, what is h of 2 giving us? Yeah, very nice, Julian. So you are basically doing 2 times x, which will be 2 times 2. And of course, that gives you 4. So 4 becomes your final answer over here. So again, in this case, we started out with the same x value of 5, but because we changed the order of our composition, you will see we ended up getting 4 as an answer. And you know, that's really important when you are thinking about these compositions, because if you switch that order around, it will not give you the same answer. Now, some functions, it is possible you could get the same answer, but for most of the time, you are not going to get the same result. So just be careful about the composition. All right, so you've looked at one example where we are using the set of ordered pairs, one example with the equations. How are you guys feeling about this? Do you have any questions? Okay, no questions. All right, let's take a look at this next example here. They're actually talking about example 4, which is this one here with the set of ordered pairs. They're saying the domain for the f function is 2, 4, and 6. And of course, you can see that 2, 4, and 6. They're saying the domain for the composition g of f came out to be 2 and 4. So they're saying basically to find the domain of your composition, you remove from the domain of f any number x such that f of x is not in the domain of g. So they're basically saying you would remove any number from the domain of your f function, which was the inside function, for any y value which is not in the domain of the g function. So you can see we have 0 and 0 over here, which we had 0 over here as the x value. But when I look at 8, there was no 8 over here, and that's why we were not able to use that 6 as our ordered sorry, not ordered pair, the 6 in part of our domain, because the 6 gives you an 8 and there's no 8 in the g function. And so that's why we were not able to use the 6 here in the composition domain. So that's just kind of what they are talking about. But if you go through the calculation, then you should also notice that with your calculation. So you can kind of use this idea they're talking about here, or basically like we showed you for 4 and 5, you can kind of use, well, 5, we didn't really talk about domain there, but for the example 4, yeah, you just go through the calculations and you will see what that composition domain comes to. Now this one, 6, is definitely asking us to find the domain for the composition. And this one, they're not asking us to evaluate at any given number. They're just saying find in general terms what your composition of f of g is going to come out to be. So they're giving us the f and g functions over here. Okay, let's do this guy. Okay, so for number 6, the f function is given as square root of x plus 3, and g of x is given to us as 3x. They're asking us to find f of g, which means f is the outside function and g is the inside function. So as I was saying, they're asking us to do this in general terms. They're not asking us for x equals 5 like we had in the previous example. So what happens here is you will literally take the g of x function and replace that in the parentheses over here. So we're going to take the 3 of x and put it inside of our f function. So that will end up giving us f on the outside, but instead of g of x, we're going to write 3x over here. Okay, so whatever is the inside function, you're going to write that entire function inside over here. So what happens now, this 3x is going to replace the x value in your f function. So that means for my f of x, I will have square root, and technically that should be x plus 3. But instead of x, you're actually going to replace it with this entire function, which was the 3x. And this is what your composition will look like, because, I mean, you can kind of factor out that 3, but I probably would just leave it as it is. So this is what our final result is going to come out to be for this composition of f of g. And this is actually what happens when you do it in generic terms. So like we started out, for the inside function g of x, we had the equation as 3x. So you're literally replacing the inside with 3x, which means now 3x will become the input for the f function, So in the f function, wherever you see the value x, replace it with 3x. If we could have simplified this function, we would have, but since we cannot, we leave it as it is. So you're done with the function definition, but now we have to talk about, okay, what is the domain of this composition going to be? And does anybody have any idea what kind of domain this square root of 3x plus 3 will have? How would we even go about calculating that? Any ideas? So it's still inside a square root, right? And what kind of restrictions do we have inside a square root? So 0 to infinity would have worked if you only had x in there, but we've also got the 3x plus 3 with it, right? So it's actually going to change a little bit from the 3x plus c, but you're kind of on the right track because remember, it's still inside a square root, which means we still cannot have a negative value inside the square root. You can have an answer of 0 and you can have a positive number. So what you have to actually do is take this inside definition that we have here, just the 3x plus 3, and 3x plus 3, that value can be 0 or greater than 0. So you're just basically solving that little inequality with the inside of the square root part. So you've got 3x plus 3, set it equal to greater than equal to 0. And what kind of x value do you see? Okay, Julian, you're getting -1. Evelyn also. Okay, so we would basically start by taking that 3, moving it to the other side. We would end up getting 3x is greater than equal to -3, right? And then of course, to get rid of the 3, get x by itself, we would divide both sides by 3. We're dividing by a positive number, so you don't have to worry about changing the direction of your inequality. And you're actually getting x is greater than or equal to -1. And Clinton, that is exactly what I was looking for. So yeah, so we are basically saying all the x values that we can use can start at -1 and anything larger than that. And just think about this. If we put -1 as our x value, you would end up getting -3 plus 3, which would of course give you square root of 0, and that would give you the answer 0. So we didn't get a negative answer. And then of course, if you go to numbers larger than that, you're only going to get positives from there. So this actually tells us that the domain of our function can basically start at -1 and go all the way to positive infinity. So it's going to be like Clinton had it, from -1 to infinity, and this is going to be the domain of our composition over here. So be very careful with radicals, especially with square roots, because as long as the inside doesn't become a negative, all the x values are acceptable. So the easiest thing to do is set it equal to greater than or equal to 0 and solve that inequality to come up with the domain of these functions. Okay. Yeah, I'm not seeing any questions pop up either. So if you don't have any questions on this, we can continue on. Okay, so we've talked about how to create compositions. They've given us the individual functions and then we've created our compositions, but you can also think of some of those complex functions, or the complicated functions we have can actually be broken down. So you can actually go in the reverse direction. So sometimes if you look at the complicated functions we have, you can break them down into simpler functions by using composition again. So they have an example over here. Capital F of x is defined as x minus 7, the whole quantity squared. So basically they are saying start with your variable x from the x, you are subtracting 7, right? And then once you subtract 7, whatever answer you get, you're going to take a square on the entire thing. So if you think of each of these operations being separate, then the first thing we are doing is we are taking our x and subtracting 7 from it. So that can become one simpler function. And then of course we are taking a square on the entire result. So you can actually think of that as being a second function. So if you do a composition between these f and g functions, you can get your capital F function. And of course, in what order you do your composition will make a difference. So here they are showing you if we did g of f, which means we're putting the x squared function on the outside, the x minus 7 on the inside, we would first start by doing g of f of x, which means take the f function and put it inside of the g function. And then of course use that to evaluate the g function, which would end up giving you x minus 7 quantity squared, which was the same thing as our capital F function. So this composition works. But what happens if instead of doing g of f, you changed it to f of g, putting the f on the outside and g on the inside? So if we're putting g on the inside, that means x squared is going inside of the f, and you will actually end up getting x squared minus 7, which is not the same thing as our f of x function. So even after you define the simpler functions, but if we don't do the composition correctly, we may still not come back to the original function that we started out with. So it's always a good idea to make sure you are checking in what order we would be doing our composition to break down a complicated function. So number 7 is what they're asking us to do is work backwards. So they're giving us a capital K of x function, which is 2 times square root of x minus 3. And they're asking us to actually break it down into a composition of 3 simple functions. So we actually have to see what kind of operations are happening over here. So let's look at number 7. We have again K of x as 2 times square root of x minus 3. And they're asking us to do this as a composition of 3 functions. So start with the x variable. What's the first thing we are doing to the x? Would you be subtracting by 3 first? Would you be taking the square root first? Would you be multiplying by 2 first? Square? I'm guessing you meant square root, Lori, since we have a square root, right? We don't have a square. Okay. But are you going to be doing the square root on the x first? Because think about if I gave you, I don't know, x equals 3. What's the first thing you would do to simplify this? Ooh, Julian, where are you getting divide from? Find the square root. So if I gave you 2 times x, and for x I'm using 3, would you actually do the square root first, or would you subtract the 3 first? Think about this, guys. What would we do first? No, we would not be doing the square first, because if you are going to be solving this, we would have to do 3 minus 3 first before we could even take the square root, because you would then be doing, oh lordy, this pen really does not want to work today. You would be doing 3 minus 3, which would give you a 0, and then you would be taking a square root. So you would be doing the square root first, sorry, the subtraction first before you did the square root. So in what order you would be solving is going to be so crucial for us to decide what this order of our composition is going to be. So the first thing to that x variable we are going to do is subtract the 3. Once we are done with the subtraction, then we would be doing the square root part. And once you are done with the square root, which would simplify the right-hand side, then we would be multiplying by 2. Because remember, you are solving where x is on the inside, so you have to work from the inside outwards in this case. Or you can think in terms of, using, please excuse my dear Aunt Sally, because right now, that square root of x is acting as a grouping symbol, kind of like how we think of parentheses. So we would need to simplify what's on the inside first. So we would be doing x minus 3, whatever that answer comes out to be first. Then we would be doing the square root, which takes care of our grouping. And then the only other thing left to do would be multiplying by 2. So x minus 3 is going to be one function. The square root of x is going to be our second function. And then the very last one is where we would be multiplying by 2. Now, which ones you assign f, g, on, or h is up to you. It really doesn't matter. What's going to matter is what the composition is going to be. So if you just stuck with, let's say the first one is our f of g function. Sorry, not f of g, f of x function. You could say the second one, and I'm just kind of going in the alphabetical order here. Our second one would be the g function. And then, of course, that means the last one would be the h function. So remember, we are working from the inside out when you are doing the composition here, which means when we try to break down our k of x function, the last thing you are going to do is multiply by 2, which means the h has to be our outermost function. The second last thing we did was take the square root, which means the g is going to be our middle function. And the very first thing that we are going to do to the x is subtract by 3, which means that f of x has to be our innermost function. So that means the order you are looking at is h of g of f for defining our k of x function. Do you guys see that? So, it's not necessarily because we defined it as f, g, and h, which means your composition is going to be f of g of h. No, it really depends on what you define these as. And then remember, we're working from inside to the outside. So the innermost function has to be the x minus 3. Then the second one after that has to be where we take the square root. So that's the middle function. And then the very last operation we would be doing is multiplying by 2, which means the 2 has to be our outermost function. So you really have to see in what order you would be doing your calculations and then work backwards from that. So that's what this composition would then come out to be. And you will have examples like this in my math lab. So any part of this that maybe you did not understand and you would like to, I don't know, maybe go over again, or if you need extra help, how are we feeling about this? Okay. Alrighty. Let's see. Not seeing anything on chat either. Okay. All right, guys. So the next thing we want to look at are these applications over here. So this one is talking about how to write the area of a square with the length of side S, which would be a function of its diagonal. So they are saying as a hint, write down your formulas for the area, perimeter, and diagonal of a square. and see if that can help us out. Okay, so let's take a look at this guy over here. So what would be the area of a square? And of course, they're telling us it's a length of side S. Okay, so maybe something like this. So our length for the side is S. And then your diagonal, they're telling us, is D. Yeah, very nice, Audrey. It is side squared, so you can basically say the area is side times side, or side squared, okay? What is the perimeter of a square? Yeah, very good, guys. It is 4 times the side, so 4 times S in this case, so that would be the perimeter. Does anybody know what the diagonal formula is? How can we calculate what the diagonal of our square here can be?
Would it be the Pythagorean theorem?
Very nice, Grace. Yeah, exactly. You want to use the Pythagorean theorem because, you know, of course, the idea is we know all 4 angles on our square are going to be the 90 degree angle. So you can basically use the idea of a Pythagorean theorem over here. So by the Pythagorean theorem, so of course, you know, the D, the diagonal would then become the hypotenuse on your right triangle, and the S and S side would basically become the 2 legs of our right triangle. So that would be, remember, it's side squared plus side squared equals the square of the hypotenuse. So that would be, of course, our side squared would be S squared, and that would equal the square of the diagonal. Now, just to clean this up a little bit, since we have S squared plus S squared, which is the same term, we can go ahead and add them together, which would end up then giving us 2S squared, and you would have D squared over here. Now, of course, we're going to need to clean this up a little bit, but let's go back to our problem over here. So they are saying, write the area of the square as a function of its diagonal, where the side of the square is the length S. So they're basically asking us to write the area as a function of the diagonal. So if you think about this, right now, our area is actually a function of the side, right? And your diagonal here, I guess we can say the diagonal is also written as a function of the side. What they're asking us is to write the area as a function of the diagonal instead of the function of the side. So how can we go about where we know the area is A equals S squared and rewrite it so that you have A equals in terms of D? And this is what we have right now for our diagonal formula. So how would you be able to rewrite where area is in terms of D instead of S? Because this is where the composition concept is coming into play. It's actually pretty simple.
Would you put the 2s squared in the A equation for D.
Okay, so do you want to send it to me on chat to see how you would rewrite that, Meredith?
Yeah, I can.
Okay, thank you. Okay, so you are saying basically rewriting it as 2s squared. Well, but that wouldn't really give us the area, right? Because you're basically saying if you write, oh, there we go. Okay, so you are given area as side squared. So just think about this. You already have s squared over here, don't you? In your diagonal formula, and we just basically want to write a in terms of d instead of a in terms of s. So what if we took our as squared, and then you have your 2s squared equals d squared for the diagonal, and just make this substitution where for the s squared, since we know s squared equals a, how about we replace that a in here for the s squared? Yeah, exactly, Meredith. That's kind of what I was looking for. Thank you. So yeah, if you make the substitution of the s squared over here with your area A, you are making that composition because now you're going from s to the a terms, which will actually end up giving us 2a, which would equal d squared then. And all you have to do is get a by itself so that you can have the area in terms of its diagonal over here. So then, of course, you would just be dividing this by 2, moving that 2 to the other side so that we could get a by itself, and you have d squared over 2. And this would now be area in terms of the diagonal, because instead of using the side, we would now be using the diagonal to find the area of our square. So, you know, this, they're kind of putting this in a composition sense, but you know, this is basically rewriting of a formula is what you are doing, because they are telling us that what if you only have the diagonal measurement? Now, one way would be you would use the Pythagorean theorem, work backwards to find what the measurement of the side is, and then use the side to calculate the area. Or if you know the diagonal, then you're just doing diagonal squared divided by 2, and that would also end up giving you the side or the area of your square instead of having to go through the side. So that's basically all they're asking you to do. So again, in this 2s squared, we basically took that s squared and replaced it with our a, because we know s squared equals a from that area definition. So you just end up getting 2a equals d squared, move the 2 to the other side, and you've got your area formula in terms of the diagonal, and that is what they're looking for here. Any of you have a question on that? Okay, I believe we have one more example over here. And this one is talking about in terms of the revenue of sale of X books at $80 each is given by the function R of X equals 80 times X. So basically each book is sold at $80. So here, X number of books multiplied by 80 will give you the revenue. Then the commission for the revenue of X dollars is given by the function C of X equals 0.10 X, and they're asking us to write the commission as a function for the number of books. So what's happening here, guys, is the revenue function that X represents the number of books. But for the commission function, the X represents the dollar amount. Now, how much commission are they getting on the sale of these books on the revenue? What does that 0.10 tell us? What percent is that commission? Yeah, very nice, guys. Yeah, exactly. It's 10% commission, right? So they're basically saying whatever is your revenue amount, $100, $200, maybe in thousands, whatever your revenue would be, the commission would be 10% out of that amount. So now they want to know, how can we write the commission where your X value, instead of being the dollar amount, is actually going to be the number of books. So any ideas how we could do the composition here so that your commission is based on the number of books and not on how much revenue you earn, or I guess the books earn? Okay. Well, that's already given to us, Julian. So what they want you to do is make a composition, because right now the way the X is given to us, this X is a dollar amount. Whereas for the revenue function, this X is the number of books. No, guys, you don't want to solve this. All you are doing is composition here. So what you are actually going to be doing is taking a composition where C of X, of course, is still going to be your outer function, because we're still, trying to rewrite the commission function. But since the revenue function is where your X are the number of books, you're actually going to put the revenue function inside of the composition function. Yeah, very good, Audrey. Plug 80x into the C function. So that means you would have the C function, which is, well, 10% of whatever the revenue is, but instead of X, you are actually going to be replacing it with 80x. Because, that's how the composition is going to happen. So what will that end up giving us? Yeah, when you multiply the 0.10 with 80x, you're basically going to end up getting 8x. So what this is actually telling us is your X now represents the number of books. And what does that 8 tell you then, guys? No, because remember the X is now representing the number of books. Yeah, Julian, that means you're actually going to get $8 for each book sold. So what happened here, instead of getting 10% commission, because that's what this 0.10 was representing, right? 10%. So of course, since we know $80 is the revenue you are getting from the sale of each book, 10% of $80 is $8. So if you sold 100 books, you would be getting, 10% of that $8,000. Or in other words, for each book sold, the agent or whoever this is going to get $8 based on each book. So you are basically just rewriting that commission function so that instead of looking at it in terms of percent and how much revenue you make, you have now converted it to where how many books you sell, you get $8 for each book sold. So now the 8 here represents the dollar amount. Okay, so you're basically just doing a composition between your commission and your revenue function. Any questions on this, guys? I know Meredith, you said you were okay. Anybody else? Okay. So this was the last example that we wanted to look at in section 2.4. So that brings us to our last section, guys, which is 2.5. And this section, as you can see, of course, is where we are talking about the inverse functions. Now, when we are talking about inverse functions, as you can see in that first statement, they're telling us one function will undo what another function does. So if you just think about these examples, we are talking about the square will undo the operation of a square root, which we've seen that since we've solved so many equations involving squares and square roots. In simple terms, you can think about addition will undo subtraction, division will undo multiplication, right? But these are just one single operation functions. But what if you have, something like we had looked at earlier, where you were doing subtraction, square root, and multiplication like we did in this k of x function. So there were three different things happening: multiplication, square root, and subtraction. So if you had to find its inverse, something that would undo all of these, well, then how would we go about figuring those out? And that's kind of where this section of inverse functions comes into play. So just to kind of explain the concept a little bit better, we have this example for pizza toppings. So they're basically saying we're ordering a pizza. The plain cheese pizza itself is going to cost $5, but then if you want to do any additional toppings, then you are basically paying $2 for each topping. So what's happening here is, as you can see, the x is going to be, what the pizza will cost, and the y represents how many toppings we're going to get on the pizza. So if you're only paying $5, then of course that means we're getting the plain cheese pizza, no toppings, so that's 0 toppings. If you're paying $11, then of course that means $5 for the basic cheese pizza, but then you are of course getting 3 additional toppings because of course you're paying $6 more for those toppings. So here the idea is the x represents the cost and the y represents the number of toppings. So if you know how much you paid for the pizza, you can go and calculate how many toppings we're going to get on the pizza. So they're talking about how there is a unique relationship because there is only one cost for the number of topping you're going to get. So it's not like you can pay $9 and get 2 toppings, and you can pay $9 and get 4 toppings, right? There's a very unique relationship. For $1 amount, there's only one number for how many toppings you're going to get. So this is what we call as the one-to-one correspondence, where you are not really seeing any repetition between your and let me get this straight, for the same y value, we cannot have 2 different x values, which means for the same number of toppings, we cannot have 2 different dollar amounts, basically. And this one-to-one correspondence that we're talking about, this unique relationship between our x and y variables, is very important when you're trying to find the inverse of the functions, when we're trying to find these inverse functions. So they are saying when you have the one-to-one correspondence between the domain and range of our function, we can say that function is a one-to-one function. If your function is not one-to-one, then we will not be able to find their inverses. So they're talking about like the dollar menu at our fast food restaurants, Wendy's, McDonald's, Taco Bell, because if you think about it, let's use McDonald's. I don't know if any of those prices have changed, but I'm kind of gonna go with what I remember. I know back in the day for $1, you could get any size drink. I don't know if that's so true. You could get one of their chicken sandwiches, I think, a fry, I'm not sure what size, and a couple bunch of other things you could get for $1. So the idea is for the same dollar amount, we can get 3 or 4 different items, right? So there's no unique relationship here. And same thing at any other fast food restaurant that have a dollar menu. So the idea is you don't have that one-to-one correspondence. And since we don't have the one-to-one correspondence, we cannot consider these functions as being one-to-one functions. So just as you look at this definition here, they're saying as long as a function has no two ordered pairs with different first coordinates and the same second coordinate, we can say the function is 1 to 1. So this definition, guys, is different from the definition you saw for what is a function. For the function definition, we said for the same first coordinate, you could not have two different second coordinates, which means for the same x value, we could not have two different y values. What this one here is saying, for the same y value, we cannot have two different x values. So it's definitely switching that order on us here. And what happens with the one-to-one correspondence is if you were to switch your x and y values like we're doing here in our pizza example, you should still be able to maintain that one-to-one correspondence, or your function should still be one-to-one. So now we are making the number of toppings our x variable, and we're making the price, the cost of the pizza, as our y variable. And of course, you can still see if we got if we know how many toppings we got, we will be able to calculate our dollar amount for the price of the pizza. So if we know we only got one topping, then we know $5 was for the cheese pizza plus $2 for that one topping. We're going to pay $7 for our pizza. If we got 4 toppings, then again, same thing, you would be paying $8 for your topping on top of the $5 for your plain pizza, and you would be paying $13. So we are able to work backwards and still calculate what the price would be if we know the number of toppings. So if you can read the first table backwards, basically, you are essentially creating a new function, which is what we call as the inverse function. So if you think of this first table being our original function, then the second table is actually its inverse function. So literally just by switching your x and y values, you are creating the inverse function in this case. And essentially that's going to be our process for finding these inverse functions. Obviously, it's going to get a little bit more complicated once we start looking at functions in terms of their equation form, but that's always going to stay true. Is by switching our x and y variables, we can find inverse functions. But guys, again, keep in mind, to be able to find an inverse function, the original function has to be a one-to-one function. If the original function is not one-to-one, there is no inverse that can be found. So just this little paragraph here is talking about as long as no two ordered pairs have the same first coordinate and different y coordinate, we call it a function. And we saw that in section 2.1 when we talked about this. Now we are saying if we interchange the x and y coordinates in each ordered pair, we may or may not have a function. Okay, so this is if you haven't checked to see if your function is one-to-one or not. However, if your original function is one-to-one, then by interchanging your coordinates, you can find the inverse function. So we can say if the function is one-to-one, it has an inverse function, or we say the function is invertible, which means you can invert it, you can find its inverse. That's basically what they're talking about here. Now we use this notation, which looks like you're doing an exponent of -1, but it's not an exponent, it's the notation that we use for inverse function. So we read it as f inverse. So again, as long as your function is one-to-one, you can find its inverse function, and that can be obtained by basically interchanging your x and y variables, or basically you are interchanging the domain and the range of your function. So just kind of keep this in mind. This is not a negative exponent. It's how you write the inverse notation. So before we get into finding inverses, this first 2 examples here are talking about, do you think you can find the inverse on these? Are these functions invertible, and why? So the first one is talking about a function that pairs the number of days since your birth with your age in years. So think about this. If you know the number of days that have passed, since we were born, would we be able to calculate our age? And what happens if you reverse that? If you know your age, would you be able to calculate the number of days since your birth? So would we consider this to be a one-to-one function or not? Okay, I'm getting yes from Audrey, Kendall, Evelyn, and Lori. Okay. Is anybody here about 20 years old? Trying to find two people who would at least have the same age over here. Kendall, you're about 20. Okay, is anybody else about 20 here? Morgan, you're 19. Okay, anybody else who's 19?
I'm 27.
You're 27. Okay, I'm trying to find two people which would have the same age. So Kendall, you're 21. Audrey, you're 24. Okay, so somebody who's 21, 24, or 19. Okay, Wyatt, you're 21. Very good. Okay, that works. So Kendall and Wyatt, we're going to use the two of you. So Kendall, can you tell me and Wyatt also what month you guys were born in? Oh, thank you, because this would be weird if you were born in the same month. My example would totally not work. All right, so one of you is August, that's Wyatt, and Kendall, you're January. So now think about this, guys. They are the same age. Would they have the same number of days since they were born? No, right? Obviously, because you can see they're both born in different months. But can it be possible for two people to be the same age and have the same number of days since they were born? Yeah, exactly. If they had the same birthday, same year and everything. I mean, obviously, the easiest example would be to think about twins, right? Two people who would be born on the same day, same time and everything. But again, randomly also, it's possible for two people to be born on the same day, same year. So in that case, we wouldn't really have that unique relationship now, would we? Because remember, we talked about that one-to-one correspondence for the same y value. We should not have two different x values. So in one direction, maybe we could make this work, but it really wouldn't work the other way around. And because of that, not having that one-to-one correspondence, you actually will not be able to find the inverse. And you know, of course, the other problem here is if you just know the person's age, how would you work backwards to find out how many days has it been since they were born? Because if they just told you I'm 24 years old, well, we wouldn't really know how many exact days it has been unless you knew the exact date and month they were born in, right? So this first one is not a one-to-one function. Oh, come on, buddy. So this would be not invertible. Okay, now what do you think about the second example here, which is talking about pairing the number of days that a deposit of $100 earning an interest of 6% compounded daily with the amount of interest. So basically we know we're depositing $100 at 6% compounded daily interest. By compounded daily, of course, means that your $100 deposit will be earning interest on a daily basis. So they're going to take that 6% and basically divide it by 365, and then whatever that number comes out to be would be how much interest you would earn every day. So they want to know if you have a function that takes the number of days and pairs it with the amount of interest you are going to earn. will that be considered a one-to-one function? Will we be able to find its inverse? Okay, so Jack, you are saying that is one-to-one. Audrey, you are saying I don't think so. Okay, so you're both giving me opposing answers. So what do we think it is? Lori, when you say yes, which one are you going with? Which side? Are they one-to-one or are they not? Okay, one-to-one. You're saying I'm stuck at the 6%. How would you trace it back with regards to that? So basically, Audrey, when they're saying it's a 6% interest, you know, if you're depositing your money, let's say $100, then basically the idea is if you know we were just doing this, let's say annually, 6% means you would be getting $6 on that $100 that you deposited, right? So they're just being a little bit more specific on how much interest you would earn. And so the amount of interest you earn is actually like the 6% is not the crucial amount. What they want to know is if you knew that this money was deposited into the bank account for, let's say, 6 months or 180 days, basically, since we're going in number of days, would you be able to calculate the interest, and would that be a unique amount? In the same way, if you knew the amount of interest your money earned, would you be able to calculate backwards and say how many days the money has stayed in the bank account? And again, would that be a unique number? Which means for the same number of days, can we get two different interest amounts? Or for the same number of interest, can we get two different number of days? Basically, that's what we're kind of trying to work through here. Okay. Because the important part here in this example is where they're telling us it is compounded daily. If it wasn't compounded daily, but it was compounded like on a monthly basis, maybe even weekly, or yearly, annually, it would be different. But since they are specifically telling us that these are being compounded daily, that means for the dollar amount, you would be able to calculate your number of days for how long your money stayed. If we know the amount of interest, we would be able to calculate the number of days. If we know the number of days, we would be able to calculate our interest. And because our interest is being compounded daily, these would be unique numbers, because for the same number of days, you will only get $1 amount, right? So if your money has been in the bank account for 180 days, you're going to have a unique amount of interest. If your money has been in the account for 181 days, you should have a different dollar amount. So this will actually be one-to-one, and that is what, let me see, Lori and trying to see, I think Jack might have been the other one who came up with that answer. So in this case, since this is a one-to-one function, we will say this is invertible, which means we could definitely find its inverse. Okay, so that's kind of the explanation you want to go through your mind. Okay, so before we get into example 3 over here, remember what they told us about the one-to-one functions. For the same second coordinate or y coordinate, you cannot have different x. So for the same y value, we cannot have two different x values. So looking at that, what can you tell me about number 3? Is it invertible or is it not invertible? So Clinton, you're saying no. Audrey, you're saying no. Yeah, because you can see we have 0, 0, 0 for all of our y values here, right? and they are all different x values. So in this case, definitely not invertible. Okay, very good. What can you say about number 4? Can we find an inverse for number 4? Yeah, because you're not seeing any repetitions here, are you? We've got 1, 1, 2, 4, 4, 16, and 7, 49. So we don't have repeating y values with different x values. So since this guy is invertible, we can find its inverse, and its inverse, and again, I'm going to use that inverse notation, is going to be, and remember, we just interchange our x and y coordinates to find the inverse function. So of course, this guy would be 1, 1 would still obviously end up staying the same. But then for the second ordered pair, you're interchanging x and y. So you would have 4, 2. We would have 16, 4. And then of course, we would have 49, 7. So that's how you're finding the inverse functions for the set of ordered pairs. So what will be our conclusion for number 5? Is it invertible or not invertible? No, because again, right here in the middle, I can see I have the same y value for 0, 0, but then I have different x values, 2 and 1. So of course, number 5, that means is not invertible. Alrighty, very good. What about number 6? Yes, it is. And what's going to be its inverse? Because obviously your y values are not repeating. All of them are different. You've got 3, 2, 5, and 6 for the y values. So it is invertible. And what's your inverse going to be? Yeah, it would stay the same, right? Because if you really think about this, guys, this is coming from your identity function. So in this case, even if we interchange our x and y values, they would obviously still end up staying the same. So it would still end up being the function itself. And, you know, of course, once we get into a little bit more detailed, we can talk about this, but just kind of a heads up for you guys to see what this inverse functions would look like. So do you have any questions at this point? Okay, so we will continue our discussion for the inverse functions next time. And once we finish section 2.5, you guys will be ready to take your exam. Just as a final reminder, guys, just please make sure that you are, you know, taking your, oops, I'm not sure what happened. Sorry about that. Just make sure you finish your homework before, you know, Monday, because I don't want you to have zeros on your homework. I know in last chapter 1, some of you did not get to finish your homework, so please finish it, okay? All right, guys, be careful, be safe, have a wonderful weekend. I will see you on Monday morning. Take care, guys. Bye-bye. Bye, everyone. Thank you.